Hello and welcome to this A-level chemistry video about rate equations. We'll start by taking a look at what rate equations are, including covering the rate constant. From there we'll move into deducing the order from both graphs and tables, and we'll finish by focusing in on the rate determining step and how that can inform us about mechanisms for a reaction. The rate of a reaction is a measure of how quickly a reaction occurs, and it can be calculated using the equation rate of reaction is equal to change in concentration divided by time. And the rate could be expressed as being the change in concentration per unit time. And this concentration change can be of a reactant or of a product. And the rate of reaction will typically have the units moles per decimeter cubed per second. The rate of a reaction is affected by a number of things. The concentration of reactants, which will be the main focus of this video, also the temperature of the chemicals at the start of the reaction, and the surface area of any solid reactants, or the presence of a catalyst for the reaction. And if the reactants are gases, pressure will also have an effect on the rate of a reaction. And this is very similar to concentration, since both pressure and concentration are linked to the number of particles per unit volume. If we know the change in concentration for a reaction and the time that the reaction takes, we can calculate the rate of the reaction. But measuring concentration is not always possible. And so we can measure the rate of a reaction by timing an observable change. For instance, we could collect a certain volume of gas, or we could observe a colour change during a reaction. Or maybe we could measure the loss in mass from a conical flash during a reaction, or time how long it takes for a solid to become too small so that we can't see it anymore. All of these quantities are either proportional or inversely proportional to the concentration, and so their values can lead to meaningful calculations about the rate of a reaction, whereby the rate might be proportional to the change in concentration over the time, but it would also be proportional to, for instance, the change in volume of gas produced over time as well. Rate equations show you how important each chemical is for the rate of a particular reaction. And we know from collision theory and from Maxwell-Boltzmann distribution curves that if we increase the concentration of a reactant, the rate of a reaction will increase. And you can see that from the Maxwell-Boltzmann distribution curve here, where we've got energy on the x-axis and number of molecules on the y-axis, and the area under the curve is proportional to the total number of molecules. And if we have the activation energy marked on the x-axis, the area under the curve to the right of this activation energy is proportional to the number of molecules with energy greater than or equal to the activation energy. And so, if we increase the concentration of a particular reactant, the curve area must increase because we've got a greater number of molecules. And as a result of that, the area under the curve to the right of the activation energy will also increase. And so we have a greater number of molecules with energy greater than or equal to the activation energy. And so the rate of the reaction will increase. The rate of a reaction is not always directly proportional to the concentration of the reactants. This is actually a simplification. It will be true for the majority of the reactions you've encountered so far. How important a reactant's concentration is in terms of the rate of a reaction is referred to as the order of reaction with respect to that particular concentration. And the order of reaction will be a numerical value, and this number will tell you how the concentration of a particular reactant will affect the reaction rate. The rate equation will give a mathematical link between the concentration of each reactant and the reaction rate. And the rate equation will typically look something like this. Rate of reaction equals K multiplied by square brackets capital A raised to the power of M, square brackets capital B raised to the power of N. And rate is the shorthand for rate of reaction, and K is something called the rate constant, which we'll come back to in a short while. The square brackets with a capital A inside is referring to the concentration of the reactant A, and this one is the concentration of reactant B. And the small m and the small n are the order of reaction with respect to reactants A and B. For A-level chemistry, the orders are restricted to 0, 1 or 2, or we might say 0, first order or second order. And it's really important to note that the order can only be determined by an experiment and not by simply looking at the chemical equation. If you wanted to determine the order with respect to a particular reactant, for instance, reactant A, you would need to do a series of experiments. And when you did the experiment, you would have to have some kind of quantity that was measurable, and you would record this quantity at regular intervals. For instance, you might record the volume of gas that had been produced every 10 seconds during a reaction. And once you'd collected the data, you would plot a graph of, for instance, volume of gas against time, and then you'd make this into a smooth curve because this is a typical rate at which the gas would be produced during a reaction. And then you would draw a tangent to the curve at the start of the reaction. So in other words, when time equals 0. And then you would find the gradient of this tangent by doing the change in y divided by the change in x. And this is known as the initial rate of reaction. And so we've followed the whole length of this reaction, but then we've used the shape of the curve to find the initial rate of the reaction from that tangent. And then you would repeat this experiment for different concentrations of A. And every time you repeated the experiment, it's really important that you would keep the other reactant concentrations constant and in excess. And this way, you know that any change you observe in the rate of the reaction is only due to the change that you have made for the concentration of reactant A. And you would do this 4 or 5 times for 4 or 5 different concentrations of A, and you would plot the graph of volume of gas against time each time, and you would plot a tangent at time equals 0 for each of these graphs, work out the gradient of that tangent, and this would give you the rate of reaction for each different concentration of reactant A. Once we have measured and recorded the rate of reaction for different concentrations of reactant A, we would plot a graph of rate of reaction on the y-axis against concentration of reactant A on the x-axis. And one of the characteristic shapes that this graph might have is like this. And this graph is showing that the rate of reaction is directly proportional to the concentration of reactant A. And we might write it more mathematically like this, where rate is representing rate of reaction, then we've got the proportional symbol, and we've got the concentration of A to the power of 1. And this is what we refer to as being first order. And a question might say, how does the graph show that this is a first order reaction? And we would say that this is a straight line graph, and it is starting from the origin, so 0, 0. And we are showing that the rate of reaction is proportional to the concentration of A to the power 1. And what this means is that if we double the concentration of reactant A, the rate of reaction will also be multiplied by 2, but raised to the power 1. And so, in other words, it will be multiplied by 2. If we quadruple the concentration of reactant A, the rate will be multiplied by 4 to the power of 1. In other words, multiplied by 4. If the concentration is made 3 times smaller, the rate of reaction will be also divided by 3 to the power 1, and that means it would be divided by 3. Keep in mind that we are assuming that whilst we've been doing this, we have been keeping the other chemicals in a constant excess, and that means that any change in rate that we observe is only down to how we've changed the concentration of reactant A. In order to find the order with respect to the concentration of reactant B, we would need to do the whole thing again, this time varying the concentration of reactant B and keeping the concentrations of all of the other chemicals constant and in excess. And then we would plot separate graphs for these reactions and use a tangent to work out the initial rate of reaction for each of the different concentrations of reactant B. Having done that, we would plot a graph of rate of reaction on the y-axis against concentration of reactant B on the x-axis. And the shape of a graph that we might find could look like this. And this graph is showing us a curve, and this curve increases with a steeper slope as the concentration increases. And this means that the rate of reaction is proportional to the concentration of chemical B squared. In other words, this is showing second-order kinetics. The rate of reaction is second order with respect to the concentration of chemical B. And what this means in a practical sense is if we double the concentration of reactant B, the rate of reaction will be multiplied by 2 squared. In other words, the rate of reaction will be 4 times larger. If we were to quadruple the concentration of reactant B, the rate would be multiplied by 4 squared, which means it would be 16 times larger. If the concentration was made 3 times smaller, the rate of reaction would be divided by 3 squared. In other words, it would be 9 times smaller. If we wanted to determine the order with respect to the concentration of chemical C, we would need to do a series of experiments where we varied the concentration of chemical C and we measured the rate of reaction on each occasion, possibly by plotting a graph and drawing a tangent from time equals 0 and working out the gradient of that tangent. And a characteristic shape that we might find when we plotted a graph of rate of reaction against concentration of chemical C could look like this. And this graph is showing a horizontal line, and it's showing the fact that the rate of reaction is not changing even though we are changing the concentration of chemical C. In other words, the rate is constant. Or we might say rate is independent of the concentration of chemical C. And this means that chemical C is 0 order. In other words, the rate is proportional to the concentration of chemical C to the power of 0. And this means that if we multiply the concentration of chemical C by 2, the rate of reaction is multiplied by 2 to the power of 0, which will in fact be 1, because anything raised to the power of 0 is 1. Quadrupling the concentration will multiply the rate by 4 to the power of 0, which is also 1. Dividing the concentration by 3 will divide the rate by 3 to the power of 0, which is also 1. And so what this means is whatever we do to the concentration of C, however we change it, the rate of reaction will be unchanged. It will always be the same, provided chemical C is the only thing that we change. You need to be able to recognize these 3 characteristic shapes for graphs of rate of reaction against reactant concentration. The first order graph, where we've got this directly proportional relationship, the second order graph, which is a curve where rate is proportional to the concentration squared, and the 0 order graph, which is the horizontal line, where rate is proportional to the concentration raised to the power of 0. And so if these results were our findings, having carried out a series of experiments, our rate equation would be the rate of reaction is equal to the rate constant multiplied by the concentration of A to the power 1, multiplied by the concentration of B to the power 2, and the concentration of C to the power of 0. This rate constant is introduced when we replace the proportionality sign from each of our conclusions from the graphs, and it would be specific to a particular temperature. Anything raised to the power of 0 is 1, And so therefore we don't show zero-order chemicals in the rate equation itself. Our conclusion being that C is a reactant in the balanced chemical equation, but its concentration does not appear in the rate equation. And vice versa. If a reactant is not in the rate equation, it must be because it is zero order. And typically we don't show the 1 as a power for the first order reactants, so the rate equation is more accurately represented like this. And why does the rate equation matter? Well, in industry, if we were trying to make a particular chemical product as quickly as possible, we would want to know that we can prioritize a particular chemical, increasing the concentration, for instance, of reactant B, in this case, would have the greatest effect on the rate of a reaction. And additionally, we can know what would happen if we were, for instance, going to double the concentration of reactant A and triple the concentration of reactant B. The rate of reaction would be multiplied by 2 to the power 1 and 3 to the power 2. In other words, 2 multiplied by 9. And so the rate of reaction would in fact be 18 times larger on this occasion. Sometimes a graph of rate of reaction against concentration can have an unclear shape. And so if we take the rate equation where rate equals K, concentration of A raised to the power of M, and the graph that I'm showing here, it isn't obvious whether this is a straight line or a curve. And so we're wondering whether this is linear and therefore first order, or whether it's curved and therefore second order. In cases like this, we can actually arrive at an answer by taking logs of the rate equation. And this gives us a new equation where the log to the base 10 of the rate of this reaction is equal to m log concentration of A plus log K, where this is of the form y equals mx plus c. And so if we plotted the log of the rate of reaction on the y-axis and the concentration of chemical A on the x-axis, this graph would be a straight line graph, and the gradient would be equal to the order of reaction with respect to the concentration of chemical A, and the log of the rate constant would be the y-intercept. And the y-intercept could be plus or minus depending on the size of the rate constant itself. You'd never be expected to derive this equation for yourself in chemistry, but you could be provided with the equation and then expected to work with it, for instance, by calculating logs, plotting the graph, or working out the gradient, and then you'd be expected to make the connection between the gradient of this line being equal to the order of reaction with respect to the concentration of a particular chemical. The sum of all of the powers to which the concentration of the reactants are raised in the overall rate equation is known as the overall order for this reaction. So for our example, where rate equals K, A to the power 1, B to the power 2, the overall order is simply 1 plus 2, which is 3. And we would say this reaction is third order overall. And this is important for a number of reasons. Firstly, it allows us to determine the rate determining step for a reaction and to determine the mechanism for an organic reaction. More about these in a different section. Additionally, it gives us a fast simplified analysis, a quick understanding of how the rate of reaction would respond to changes in the concentration of the reactants. For instance, for a third order overall reaction, if we doubled the concentration of all of the reactants, the rate of reaction would be multiplied by 2 to the power of 3. In other words, the rate of reaction would be 8 times larger. Moving beyond the scope of A-level chemistry, the overall order of reaction is also useful for comparisons between different methods of doing a particular reaction. It's also useful for designing experiments, particularly in something called computational chemistry, which is used for kinetic modelling. Catalysts increase the rate of a chemical reaction, but they are unchanged by the chemical reaction itself. Any chemical that appears in the rate equation is important when determining the rate a reaction occurs at. And so this means that a catalyst must appear in the rate equation. But they are not typically shown in the chemical equation, since that will only show the chemicals which undergo a change, and catalysts do not change. And so something can be in the rate equation, but not in the chemical equation. For instance, in the chemical equation that I'm showing here with the reaction between iodine and propanone, this is the chemical equation, but the rate equation will show that rate equals K, propanone concentration to the power 1, and hydrogen ion concentration also to the power 1. And so we can see that this is first order with respect to propanone, and first order with respect to the hydrogen ions, which were not shown in the chemical equation. And this is suggesting that this reaction is acid catalyzed and the hydrogen ions are acting as a catalyst. And the rate equation is in fact also showing that iodine is not present, and therefore we must assume that it is zero order and its concentration is not affecting the rate of reaction. During chemical reactions, it is very common to have one chemical as our limiting reagent and the other chemical is present in excess. If the concentration of a reactant is significantly larger than the concentration of another reactant, its concentration is only going to change by a very small proportion. In other words, we can consider that change to be negligible, and therefore the concentration of this chemical that is present in excess can be considered to be effectively constant. And that means that the concentration of this chemical is unlikely to have any effect on the rate of reaction. And so this means that this chemical can be considered to be zero order. And so any chemical present in excess would not appear in the rate equation. It is possible to deduce the order with respect to a particular chemical from a graph of reactant concentration on the y-axis versus time on the x-axis, where the shape of the curve provides an indication of the order. To determine the concentration of reactant at a particular time, it's first necessary to set up the reaction mixture and start the reaction, and at the same time start a timer. And then, at regular time intervals, remove a sample from the main reaction mixture in order for you to be able to measure the leftover reactant concentration. Depending on the type of reaction you are observing, it might be necessary to do an additional step every time you remove a sample from the main reaction mixture, because there is a good chance that this reaction would continue just on a smaller scale in the new vessel that you've put the reaction mixture into. And so we need to stop this reaction from continuing, and this process is known as quenching, and this can be done in a variety of different ways. For instance, you might place this withdrawn sample into a container of ice, and that would drop the temperature such that the rate of reaction would drop to almost zero. Or you might significantly dilute the sample that you have withdrawn by adding a lot of water to the sample. Or, depending on the reaction, you might, for instance, neutralize one of the chemical reactants that you're not going to be measuring the concentration of. And this means that you can then analyze the concentration of your chosen reactant, for instance, by doing a titration, and you don't need to worry that this reaction is still continuing. When we plot a graph of concentration against time, one of the characteristic shapes that we might observe could look like this. And what we're seeing here is a straight line showing a constant decline in concentration. And the gradient of this line would be change in concentration divided by time. And so that means the gradient of this line is equal to the rate of the reaction. And this graph is a characteristic of a zero-order reaction. And the reason for this is the gradient is unchanged as the reaction proceeds. And so even though we are seeing a decreasing concentration of reactant as the reactant gets used up, this is not affecting the rate of reaction. That concentration is decreasing at a constant rate, and so the rate of reaction is constant. And so we can see from this shape that this is characteristic of a zero-order reaction, because over time the reactant concentration is decreasing, but the rate of reaction is not. And so the rate of reaction would be equal to the rate constant multiplied by the concentration of reactant raised to the power of 0, but then raising something to the power of 0 is 1, and so the rate is equal to the rate constant. And so for a graph like this, the gradient will always be equal to the rate of the reaction, but for a zero-order reaction, the gradient is also equal to the value of the rate constant. And this is something that you might be asked to calculate in an exam question. The concentration versus time graph for a first-order reaction shows a slightly sloping curve with a constant half-life. You'll be familiar with the term half-life from radioactivity, but in this context, what we mean is the time taken for the concentration of a particular reactant to halve. And for first-order reactions, the amount of time taken for the concentration to halve is constant. And you can see this from the graph. When we start with a concentration of, for instance, 2, the amount of time taken for it to halve and turn into a concentration of 1 is this distance, and then that concentration will halve again and be 0.5, and that takes the same amount of time to happen, and then if the concentration halves again, this takes the same amount of time. Not only can you recognise first-order reactions from the shape of the curve itself, the order can be found by drawing tangents to the curve. Then you can calculate the gradients of the tangent, and this will give you the rate of reaction at that particular reactant concentration. And so if we draw a tangent at the start of this reaction, when the concentration of a chemical A was 2.0, we might find the gradient of this tangent, i.e. the rate of reaction, is 3.6 moles per decimeter cubed per second. And then we would draw a tangent when the concentration of A is 1 mole per decimeter cubed, and we might find that this rate of reaction is 1.8 moles per decimeter cubed per second. And so what we've found here is that the concentration of reactant A has been halved, and the rate of reaction has also been halved. And this is a characteristic of a first-order reaction. A graph of concentration against time for a second-order reaction shows a curve that declines steeply at first and then begins to level out, and it will have an increasing half-life. In other words, the amount of time taken for the concentration of a reactant to halve will increase as the reaction goes on. And this makes sense from the point of view of this being a really consequential chemical in terms of the rate of reaction. And so when its concentration has decreased, the rate of reaction would logically be much, much slower because there is less of this important chemical present in the reaction mixture. And we can see this here when the concentration changes from 2 to 1, this takes a certain amount of time. When it changes from 1 to 0.5, it takes more than double the amount of time. And when it changes from 0.5 to 0.25, it takes a further increase in amount of time for this change to occur. And this is characteristic of a second-order reaction where rate is equal to the rate constant multiplied by the concentration of the chemical raised to the power of 2. The order can again be found by drawing tangents to this curve and calculating the gradients of the tangents, which gives us the rate of reaction at that particular reactant concentration. For instance, when chemical B has a concentration of 2 moles per decimeter cubed, the gradient might be found to be 4.8 moles per decimeter cubed per second. And then if we drew a second tangent when the concentration was 1 mole per decimeter cubed, the rate of reaction might be found to be 1.2 moles per decimeter cubed per second. And from these two illustrative numbers, we can see that when we halve the concentration from its starting value, the rate of reaction is 4 times smaller. And this proves the second order relationship where rate equals Kb concentration squared, which is very powerful because the difference between a first order curve and a second order curve is not always easy to see just by observing the curve itself. The rate constant, given the symbol lowercase k, is a constant that links the concentrations present in the rate equation to the rate of reaction. And the rate of reaction is proportional to the value of the rate constant, which means that the larger the value for the rate constant, the faster the rate of the reaction. The value of K will vary with temperature, and so when you're given a rate constant in an exam question, it will normally be stated as being at a particular temperature. And it is the case that the larger the temperature, the larger the value of the rate constant. And this makes sense. For instance, if you consider the graph of rate of reaction against temperature, we might see a shape looking like this, and we can see that as temperature increases, rate of reaction increases, which makes sense as reactions take less time. This increase is an exponential increase, and this is because many, many more particles will have energy greater than or equal to the activation energy for this reaction. And so, a corresponding graph of rate constant K against temperature will have the same shape, since the rate of reaction is proportional to the rate constant. Now, the precise shape will vary, but we'll definitely see a curve like this, up to a point, and after a certain point, the rate of reaction and the rate constant will level off and flatten out, as other factors might limit the rate increase for this particular reaction. When given a rate equation, you could be expected to calculate a value for the rate constant or to work out what the units would be for the rate constant. In order to calculate the value for the rate constant, you would need to either substitute values into the rate equation and then rearrange the equation and solve it for K, or first rearrange the equation, then substitute values in, and then calculate the value for K. You'd obviously get the same answer both times. And so, for instance, for the rate equation that I'm showing here, if we rearranged this to make K the subject of the equation, we would have K equals rate of reaction divided by concentration of A to the power of 1 multiplied by concentration of B to the power of 2. To calculate the units for the rate constant, you need to use that same rearranged equation and then instead of substituting numbers in, substitute in the units. The rate of reaction will always be moles per decimeter cubed per second for a question like this, and the units of concentration will always be moles per decimeter cubed. And so on the top of the expression we have moles per decimeter cubed, and then because this is a third order reaction overall, we will have 3 units for the concentration. And then we need to simplify this down by cancelling out terms that appear on the top and the bottom of this fraction. So that's 1 lot of moles and 1 lot of dm minus 3, and then combine those terms on the bottom of the expression where moles multiplied by moles is mole squared, and dm minus 3 multiplied by dm minus 3 is dm minus 6. And so we have this 2-line fraction for the units of the rate constant. And we need our units to be all present on one line, so we need to bring mole squared up to the top, and that changes the power from positive to negative, and dm minus 6 comes up to the top and becomes dm6. And so the units for this rate constant for this third order overall reaction is mole minus 2 dm6 seconds to the minus 1. If you'd prefer, you can actually remember the units for the rate constant based on the overall order for the reaction. For instance, 0 order reactions have the units of moles per decimeter cubed per second, and that makes sense because there's no concentration terms in the rate equation. First order overall would have the units of seconds to the minus 1. Second order overall would be mol minus 1 dm3, seconds to the minus 1. Third order, as we've seen, and fourth order would be mol minus 3 dm9, seconds to the minus 1. Remembering this is sometimes easier than working it out, and you can see that there is a progression in terms of how the moles term and the dm term changes as we increase the overall order for the reaction. It's very common for exam questions to give you tables of results where somebody has repeated an experiment multiple times for different concentrations of the reactants each time, and they are showing the rate of reaction being different for each of these experiments. And you could be expected to work out either what is the order with respect to the particular reactants or what is the rate equation. And the way that we have to do this is we have to compare pairs of experiments, trying to find pairs where only one concentration has changed each time, explore how that concentration has changed, and compare that to the change in the rate of reaction. For instance, if we compare experiments 1 and 2, we can see that the concentration of chemical A is 3 times larger in experiment 2 than it was in experiment 1. The concentration of B has not changed each time, and so the only thing that can be affecting the rate of reaction is this tripling of the concentration of chemical A. And then we see that the rate of reaction has also tripled, and that means that we're seeing that this is first order with respect to the concentration of A, because the rate of reaction has been multiplied by 3 to the power 1. And then if we compare experiments 2 and 3, we can see that the concentration of A is the same in both experiments, and the concentration of B has been doubled. And that means that the fact that this rate of reaction is changing is only down to how we've changed the concentration of B. And in fact, the rate of reaction has got 4 times larger, even though we were only doubling the concentration of B, which means that it must be second order with respect to B, because the rate of reaction has been multiplied by 2 squared. And so the rate equation is rate equals K, concentration of A to the power 1, multiplied by the concentration of B to the power 2, and so this is third order overall. Here we're being shown a series of 4 repeats to an experiment in a reaction between chemicals X, Y, and Z. We've got different starting concentrations of each of those chemicals, and a different rate of reaction was measured for each of them. And we need to work out what the order is with respect to each of these chemicals and what the overall rate equation is. And so if we compare experiments 1 and 2, the only difference in starting concentrations for the 3 reactants is that X is 4 times larger. And then the rate of reaction is actually the same. And that means that this rate has been multiplied by 4 to the power of 0. In other words, this is 0 order with respect to the concentration of X. And then if we consider experiments 2 and 3, the only difference this time is that the concentration of Y has been tripled, and the rate of reaction has changed from 4 to 36. And so it's definitely not 0 order this time because the rate has changed, and it isn't first order either because that would make the rate turn into 12. What has happened is that the rate of reaction is 9 times larger, or it has been multiplied by 3 squared. And therefore we can conclude that this is second order with respect to the concentration of Y. And then finally, if we consider experiments 2 and 4, the only change this time is that the concentration of Z is 4 times larger, and the rate of reaction is also 4 times larger, or it has been multiplied by 4 to the power of 1, and therefore it is first order with respect to the concentration of Z. And so the rate equation here would be rate equals K, concentration of Y to the power 2 multiplied by the concentration of Z. Remember, when a chemical is 0 order, it is not included in the rate equation. And this reaction would be third order overall. In this table, we're shown 3 repeated experiments for the reaction between chemical A and B and different rates of reaction each time. And we need to work out what the order is with respect to A and B, and therefore what the rate equation is. First of all, let's take a look at experiments 1 and 2. The difference between those 2 experiments is that the concentration of A is 4 times larger. The concentration of B is constant, so we can ignore that. And the rate of reaction has changed from 2 to 8, and so it is 4 times larger as well, or we could say it's been multiplied by 4 to the power 1, therefore proving that this is first order with respect to the concentration of A. And then we have a bit of a problem because there is no pair of experiments where the concentration of A is constant. And so what we need to do here is work out what the effect would be if only the concentration of A was changed. And so if we pick experiment 2 and 3, the concentration of A has been changed from 4 to 12. In other words, it is 3 times larger. If this was the only thing that was changing, the rate of reaction would increase by 3 to the power of 1, so 3 times larger, and that means it would change to 24 if only the concentration of A was changing. However, we can see that it is not 24 because the concentration of B has changed as well. It has been doubled. And what we can see is that this value of 24 is actually doubling up to 48. And so that means that the concentration of B is being doubled and the rate of reaction is being multiplied by 2 to the power 1, meaning that this is first order with respect to B. And so the rate equation shows rate equals K multiplied by the concentration of A to the power 1 and multiplied by the concentration of B to the power 1, showing that the reaction is second order overall. In this table, we're being shown repeated experiments for the reaction between chemical P and Q with different starting concentrations of the reactants for each experiment. And we're being shown different rates of reaction each time, and we need to use the information to work out what the order is with respect to P and Q and what the overall rate equation is. If we compare experiments 1 and 2, we can see that the concentration of Q is the same each time, and the concentration of P has been tripled. And then the rate of reaction has been multiplied by 9, because 36 is 9 times bigger than 4. And that means that the rate of reaction has been multiplied by 3 squared, and so therefore we can conclude that this is second order with respect to the concentration of P. And then we have a problem because the concentration of P has changed again, and so we can never consider a pair of experiments where that concentration is constant. And so what we need to do is pick a pair of experiments and imagine what would happen if only the concentration of P had changed and work out what that would do to the rate of reaction. And so if we consider experiments 2 and 3, that changes the concentration of P by 2. And since P is second order, that would quadruple the rate of reaction by multiplying it by 2 squared. And so if the concentration of P was the only thing that was changed, the rate of reaction would be multiplied by 4, and so it would turn into 144. However, we have also tripled the concentration of Q, and this has in fact done nothing to the rate of reaction. The rate of reaction is still 144, even though we haven't factored in this tripling of Q. And that means that Q must be 0 order, because the rate of reaction has been multiplied by 3 to the power 0. In other words, it has been multiplied by 1. And so the rate equation this time is simply rate equals K, concentration of P squared, and the reaction is second order overall. Sometimes we can be presented with a table of data for repeated experiments for different starting concentrations of the reactants and different rate of reaction. And we might be given the rate equation. And this time we might be asked to fill in the table for missing concentrations of one or both of the reactants or missing rate of reaction. For instance, you can see that in experiment 2, the rate of reaction is missing, and experiment 3 is showing a missing concentration of X. And so if we compare experiments 1 and 2, you can see that the concentration of X is being doubled and the concentration of Y is being multiplied by 4. Now, since X is shown in the rate equation as being second order, doubling its concentration will quadruple the rate, because 2 squared is 4. And so this would change the rate from 4 into 16 if the only thing that was being changed was the concentration of X. But we are also changing the concentration of Y by a factor of 4. And so that means that the rate of reaction would be multiplied by 4 to the power 1, and 16 multiplied by 4 is 64. And so the new rate of reaction would be 64. And then if we compare experiments 1 and 3, we can see that the concentration of Y is unchanged in these two experiments, but the rate of reaction has been multiplied by 100. And so the rate has been changed by 100, the concentration of Y is unchanged, and so that means that whatever we've done to the concentration of X has been squared and then applied to the rate. And so the change in the concentration of X must be equivalent to the square root of 100, which is 10. And so that means that the concentration of X must have been multiplied by 10, and then 10 squared is 100, and this explains why the rate of reaction is 100 times larger. And so this new concentration of X must be 20. If we've been provided with a rate equation and an incomplete table for different experiments with different starting concentrations of reactants and different values for the rate of reaction, we could work out the value for the rate constant and then use this constant along with the rate equation to work out our missing values. For instance, if we take experiment 1, we can work out the value of K by taking the rate equation and substituting in the rate of 60, the unknown value for K, the concentration of M is 3, and the concentration of N is 5. And therefore the value for the rate constant could be found by taking 60 and dividing it by 3 times 5, which gives us a value for the rate constant of 4 moles to the minus 1, dm3 seconds to the minus 1. And we can then take this value of K that we've calculated and use it to work out the unknown rate of reaction in experiment 2. Because rate equals K, concentration of M times concentration of N, so therefore the rate will be equal to 4 for the value of K, multiplied by 7, multiplied by 12, which would give us a rate of reaction of 336. And then in experiment 3, we have an unknown concentration of N. The rate equation tells us that rate equals K, concentration of M times concentration of N, and so 240 is equal to 4, multiplied by our known concentration of 6, and then multiplied by our unknown concentration of N. And then this rearranges to the concentration of N being equal to 240 divided by 4 multiplied by 6, which gives us 240 divided by 24, which means our unknown value for the concentration of N is 10. Some chemical reactions happen over several steps rather than all at once, and the rate equation can inform us about the mechanism of multi-step reactions. This doesn't usually mean mechanism from the point of view of nucleophilic substitution or elimination, but rather which step out of all of the steps is the slowest. And for multi-step reactions, the slowest step is called the rate-determining step. As a metaphor, imagine 3 people were writing cards, and each has their own dedicated job. In step 1, this person has to make sure the card is angled in portrait position, and then they pass it on to person 2. In step 2, this person writes many thanks and draws a quick picture on the card, and then they pass it on to the next person. And then in step 3, this person folds the card ready to post it. It's clear from this example that person 2's job takes the longest, and all the steps have got different speeds. And so how quickly person 2 does their step will determine the rate of the whole process. And if the people writing cards had an extra person to help, you'd ask them to help with step 2. And this is the same with chemical reactions. If you want to speed up a chemical reaction, you would focus on speeding up the rate determining step. And so chemicals that are reactants in the rate determining step will be in the rate equation. And from the other perspective, if a chemical is not in the rate equation, it is not a reactant in the rate determining step. The chemical equation shows the overall changes that occur during a particular reaction. And so we might have 2A plus B plus C reacting together to produce D plus E plus F as our chemical equation. But the reaction mechanism might show that this reaction occurs in successive steps. In step 1, A plus B react together and produce D. In step 2, A plus C react and produce E plus F. And so overall, the chemical equation represents the changes that occur, but this has taken place over several steps. And perhaps step 1 is the slow step, known as the rate determining step, and step 2 is relatively fast. The reactants for the rate determining step will be the chemicals that appear in the rate equation. And so the rate equation will show rate equals K, concentration of A, multiplied by concentration of B. And the orders shown in the rate equation as powers match the coefficients or the multipliers for the reactants in the rate determining step. And so because there is only one A and one B in step 1, the rate equation will show A and B both being first order. In the chemical equation, where 3A reacts with 2B and C to produce X plus Y plus 3Z, we might be showing a reaction mechanism taking place over 3 steps, as I'm outlining here, where step 1 is fast, step 2 is the rate determining step, and step 3 is also fast. Now what we're seeing here is that 2A plus H plus are reacting in the rate determining step. But when we compare those reactants to the chemical equation, we see that H plus is not appearing in the chemical equation. And this is suggesting that H plus is a catalyst, and acid catalysts are common to organic mechanisms. And we can prove that this is a catalyst because the H plus is being used in step 2, but it is being regenerated in step 3, which is part of the definition of a catalyst. It is speeding up a reaction without actually being changed overall itself. Now, catalysts appear in the rate determining step, so that means that they must appear in the rate equation, but they don't appear in the chemical equation. And so that means that our rate equation here will show rate equals K, concentration of A raised to the power 2 multiplied by concentration of H plus. And this is reflecting the fact that the rate determining step is showing 2 of A and only 1 of H plus. So it's second order with respect to A and first order with respect to the acid catalyst. In this chemical equation, 2x plus 2z is producing B plus C. And the reaction mechanism is showing that this actually takes place over 3 steps, with the first and the third being the fast steps, and the second step being the slowest, and so it is known as the rate determining step. And as we know, the reactants for the rate determining step are the chemicals that appear in the rate equation, and the orders or the powers in the rate equation match the coefficients from the rate determining step. But here we have a problem because we've got chemical Y as a reactant in step 2, but chemical Y is not a reactant in the overall chemical equation. And in fact, chemical Y is an intermediate chemical, and that means it is made during the reaction itself and then used up in a later part of the reaction. And since it is not possible to monitor the concentration of intermediate products accurately, they do not appear in the rate equation. Instead, the rate equation includes molecules from previous steps that are responsible for making the intermediate product. And so in step 1, X plus Z react together to produce Y. And so therefore, one X and one Z are needed to make Y, and so they can be considered to be equivalent to Y, and so the rate determining step is effectively saying 2X plus Z are the reactants. And so therefore, the rate equation will be showing rate equals K, X squared, because X effectively appears twice in the rate determining step, once by itself and once in Y, and then Z to the power 1, because Z also appears in the rate determining step as a chemical that's required to make the intermediate. We might be presented with a chemical equation and a series of steps constituting the reaction mechanism, and we might also be given the rate equation, and we could be asked to identify the rate determining step in this mechanism. And so in this example, the rate equation is showing rate equals K, X to the power 1, Y to the power 2. So first order with respect to X and second order with respect to Y. And we need to remember that the orders or the powers in the rate equation match the reactant ratio in the rate determining step. And so we are looking for the step which contains 1 molecule of X and 2 molecules of Y. And this means that step 2 must be the rate determining step, since the reactants in that step are in the same ratio or proportion as the powers or the orders in the rate equation itself. Or you could personalize it to this situation and say X and Y appear in the same ratio as their orders in the rate equation. Or maybe even better, saying step 2 contains 1X and 2Y, which matches their orders in the rate equation. Knowledge of rate equations and rate determining step can support our understanding of how organic mechanisms can occur. For instance, if we consider the nucleophilic substitution, where bromoethane can react with sodium hydroxide in aqueous solution to produce ethanol. There are in fact 2 possible mechanisms under which this could occur, but both of them are nucleophilic substitution. In one of the mechanisms, the hydroxide ion can act as a nucleophile and directly attack the electron-deficient carbon in the halogenoalkane. This step is quite slow, and it involves the formation of an intermediate chemical where the hydroxide ion has partially bonded to the carbon, and the bond between the carbon and the bromine has partially broken. And then this step is followed up by the fast step where the bromine to carbon bond continues to break and the oxygen to carbon bond finishes forming. And so because we have got these 2 chemicals on the left-hand side involved in the step that is slowest, the rate determining step, the rate equation will be rate equals K, halogenoalkane concentration to the power 1, hydroxide ion concentration to the power 1. In the second option, we still get nucleophilic substitution occurring, but first the halogen breaks its bond to the carbon, and this produces a carbocation in a slow step, the rate determining step. And then in part 2, the hydroxide ion nucleophile attacks the carbon in the carbocation, and we produce our alcohol. And this second step is much faster. And since the first step is the rate determining step, and this only includes the halogenoalkane, that's the only chemical that appears in the rate equation. Since there are 2 possible mechanisms for this hydrolysis of bromoethane reacting with the hydroxide ions, we need some way of differentiating them. And so the first mechanism, which showed 2 molecules in the rate determining step, and was therefore second order overall, is known as substitution nucleophilic with a 2, and we'd say it is SN2. And the second mechanism that we saw had only 1 molecule in the rate determining step, and so it is first order overall, and we refer to this as SN1, substitution reaction, nucleophilic mechanism, 1 chemical in the rate determining step. And so this means that if we do an experiment where we determine the order with respect to a particular reactant, in this instance, the hydroxide ion is all important because it is either first order or 0 order. we can determine whether SN2 is occurring if the hydroxide ion is first order, or SN1 if the hydroxide ion would be zero order. For this particular example, there is a tendency for primary or straight chain halogenoalkanes to undergo the SN2 mechanism, and for tertiary, or in other words branched halogenoalkanes, to undergo the SN1 mechanism. Okay, that's the end of this video. Thanks for listening.